Okay, so now that we have congruence modulo m, and now that we know a few facts about them, it's time to start looking at some applications of those things, and that's going to be a whole laundry list of topics. Well, let's take a look at the list. So, congruences can be applied in many situations. Among them are divisibility tests for mental arithmetic, and personal opinion, yeah, children should learn divisibility tests, maybe not in their full abstract glory as we will see them, but certainly at least some of them. Determining which day of the week any given date was, so a perpetual calendar, and that used to be a vaudeville act. At least I remember seeing an act on TV where a guy would just tell people on what day of the week they were born. Setting up round-robin tournaments, well, that's something where, because I grew up following German soccer, I'm somewhat biased, and I still think that that is the fairest way to determine a champion, because when everybody has to play each other, and if you don't do that in a neutral location, maybe even with home and away games, well, then there's really nobody can say, well, we had a bad day, because if everybody plays everybody, well, then everybody will have a bad day every so often, and the ones who don't are the ones who are champions, and they're champions for a reason. Hashing functions. Well, hashing functions are something from computer science. Those things compress a range of numbers into a more manageable range of, by and large, distinct numbers. And so that means there are real applications of congruence modulo m also. I mean, if we're looking at this, mental arithmetic is nice, but we do have computers for the big stuff, and especially in number theory with the hundreds of digits isn't done mentally anymore, at least not with the numbers themselves. Similarly, which day of the week any given date was, well, yeah, it's a vaudeville act, and round-robin tournaments, it's wonderful entertainment, but even as much as we may like our sports teams, it's still entertainment, right? And even though it's competitive entertainment, okay, let's not try to insult anybody. And then a final application that we're going to look at will be check digits on UPC and ISBN codes to make sure, or at least highly likely, that a code is valid. And that is, of course, another real application here. Okay, so let's talk about divisibility tests. Here's where we can actually prove some theorems, and that'll take about half the slides in here. Basically, the idea for the divisibility tests, which is going to follow us throughout everything we're going to prove here, is very, very simple, and that is when two numbers are equivalent modulo m, and there is another number that divides the modulus, well, then d divides a if and only if d divides b, and that's very simple, because when a is equivalent to b modulo m, then a is q times m plus b, so any number d that divides m and one of a and b must also divides m and one of a and b must also divide the other number. Okay, so here's the first theorem. If you take an integer that is divisible and you want to know whether it's divisible by 2 to the j, we can say that that is the case if and only if its last j digits in the usual base 10 representation are divisible by 2 to the j. So that's basically the old rule: a number is divisible by 2 if and only if it ends in 2, 4, 6, 8, or 0. Of course, by now divisibility by 2 should be so second nature to us that we shouldn't even have to worry about that, but that's basically what's behind the divisibility test. And the proof, well, let's see. We know that 10 is divisible by 2, and that means 10 to the j is divisible by 2 to the j. And so now if we let a be q times 10 to the j plus b, well, then a is equivalent to b modulo 10 to the j, right? And the base 10 representation of b is comprised of the last j digits of the base 10 representation of a. And of course, we also know that a can be written in this fashion because this is nothing else but the division algorithm. And so that means that a is divisible by 2 to the j if and only if b is, because they're equivalent, and the base that we're dealing with here, the modulus, is divisible by 2 to the j. And that's already it. Well, in practice, it's probably still easy to divide by 2 until that's no longer possible, but nonetheless, that is a first test here. If we're looking at another divisibility test that certainly is more effective than long division, especially when you've got really longer numbers, 5 digits, 10 digits or so, is that an integer n is divisible by 3 if and only if the sum of its digits in the usual base 10 representation is divisible by 3. Well, that and a similar result actually holds for 9 also. I don't think I've ever learned that one in school. I just checked if it's divisible by 3, and if it is, I checked again. But that is certainly a standard divisibility test. And, well, why is it true? The proofs for division by 3 and by 9 will actually be virtually the same, and so we will focus on the division by 3. And what do we have? We will first prove by induction on j that 10 to the j is equivalent to 1 modulo 3. That should be something that doesn't sound too bad, because the number before 10 to the j has a bunch of 9s, and that's divisible by 3. If we want to look at it more abstractly, we use induction. And the base step for j equals 0 is trivial, because 10 to the 0 is 1. And for the induction step, we note that 10 to the j plus 1 is minus 1 is, of course, just 10 to the j plus 1 minus 10 to the j plus 10 to the j minus 1. And we know that that one is divisible by 3 already, because that 10 to the j is equal to 1 modulo 3. And for the other one, we know that, well, if we factor out a 10 here and subtract, and 10 minus 1 is 9, so we end up with 9 times 10 to the j plus 10 to the j minus 1, and that is divisible by 3, which means that 10 to the j plus 1 is equivalent to 1 modulo 3. Now we can note that, well, our number, if we write it out in the base 10 notation, is just n equals sum j equals 0 to k minus 1 n sub j 10 to the j, which modulo 3 is equivalent to the sum j equals 0 to k minus 1 of the digits themselves. And so that means that n is divisible by 3 if and only if its sum of the digits is divisible by 3, because the two are equivalent modulo 3. And for division by 9, we can also see the only thing we have to do is use a 9 instead of a 3, and because we have a 9 here, the whole argument will work out in exactly the same fashion. Alright, what else do we have? We can talk about divisibility by 11, and I have to honestly admit I have never learned an algorithm or a check for divisibility by 11, but a number is divisible by 11 if and only if the alternating sum a0 minus a1 plus a2 and so on of its digits in the usual base 10 representation is divisible by 11, and by now we ought to know how that goes, right? Somehow we have to show that this sum is equivalent modulo 11 to the number itself. Alright, so first we prove by induction that for all non-negative numbers j, we have that 10 to the j is equivalent to negative 1 to the j modulo 11. And the base step for j equals 0 is again quite trivial, because if you take two numbers and raise both of them to the zeros, you end up with 1 on both sides. For the induction step, we take a look at 10 to the j plus 1, and we know that that is 10 times 10 to the j, which is equivalent to negative 1 times negative 1 to the j, which is negative 1 to the j plus 1 modulo 11. I think here I have to be careful, because, well, I have to justify that 10 is equivalent to negative 1 modulo 11, but I think that's pretty clear because their difference is 11. Alright, either way, that means that if we write our number in the typical base 10 expansion, that the 10 to the j's, when we work it modulo 11, break down into negative 1 to the j's, and all of a sudden the number n is equivalent modulo 11 to the alternating sum of its digits, and that means n is divisible by 11 if and only if the alternating sum of its digits is divisible by 11, and that's it. So that's pretty neat. How far can we push that if you're looking at divisibility by hard prime numbers like 7, 11, or 13? Okay, we've got something for 11, but we don't have anything for 7 or 13, and certainly I didn't learn divisibility tests for 7 or 13 in school, but apparently that's possible too. So an integer n is divisible by any of these three numbers if and only if the alternating sum of 3-digit blocks in the base 10 notation is divisible by 7, 11, or 13. Well, we group, we figure out if it's somehow equivalent modulo 7, 11, or 13 and move on, right? Same proof as before. So, proof. Again, the proofs for division by 7, 11, and 13 are similar, so we focus on division by 7. And we first prove by induction that for non-negative j, we have that 10 to the 3j is equivalent to negative 1 to the j modulo 7. We can see that the familiar pattern emerge here, right? 10 to the 3, that's the base that we have if we start grouping base 10 digits by 3. All of a sudden, we're looking at one of those group digits having a valuation in a base 1000 notation, if you will. And if we can show that those things are negative 1 to the j, well, then we're doing quite fine again. So the base step for j equals 0 is again trivial. For the induction step, we note that 10 to the 3 times j plus 1 is 1000 times 10 to the 3j. And we know modulo 7, well, modulo 7, 10 to the 3j by induction hypothesis is negative 1 to the j. And we're also claiming that 1000 is equivalent to negative 1 modulo 7. That would mean that 1001 is divisible by 7. How would you do that? 1001, well, divide 10 by 7, you end up with 300 being left. Divide 30 by 7, divide 1001 by 7. Okay, divide 10 by 7, you end up with 3, you keep 301. Divide 30 by 7, you subtract 28, you keep 21, and 21 is divisible by 7. Okay, so that means that this really works out. And well, now we do the same thing as before. N is the sum, if we're working out things in blocks now, the sum j equals 0 to k minus 1 of these 3-digit base 10 blocks times 10 to the 3j. But 10 to the 3j is equivalent to negative 1 to the j modulo 7, and that means n is divisible by 7 if and only if its alternating sum of 3-digit base 10-digit blocks is divisible by 7. And we can see that the argument will work the same way for 11 and 13. It will hinge upon the fact that 1000 is equivalent to negative 1 modulo 11 and modulo 13, and I let you work that out. Okay, so if we want to talk about this in general, we could say if we have that d is a divisor of a base r, then an integer a is divisible by d to the j if and only if the number aj minus 1, aj minus 2 all the way through a 0 of its last j digits in the base r representation, that all those are divisible by d to the j. And it's the same proof as what we did for 2 to the j, right? So if r is divisible by d, then r to the j is divisible by d to the j. So we can say if we have two numbers, we can divide a by r to the j. We end up by division algorithm that a is q times r to the j plus b. And a is equivalent to b modulo r to the j, therefore. And the base r representation of b are the last j digits of the base r representation of a. And a is divisible by r to the j, it should be here rather than r, and if and only if b is. Let me fix this real quick. And we're back. Well, okay, so a is divisible by r to the j if and only if b is. And that's the end of that one. We can also, okay, so note, however, that if we needed to get the base r representation, that should be an r, but we're moving on anyway, we would need to perform divisions to get that representation to begin with. Okay, well, if we have that d divides our base minus 1, then an integer n is divisible by d if and only if the sum of its digits in the base r representation is divisible by d. So that is the abstract analog of the division by 3 result that we have. And the proof goes the same way, right? So we prove by induction on j greater or equal than 0 that r to the j is 1 modulo d. Well, the base step j equals 0 is trivial. And for the induction step, we realize that r to the j plus 1 minus 1 is r to the j plus 1 minus r to the j plus r to the j minus 1, which is r minus 1 times r to the j plus r to the j minus 1. And now we know that r to the j minus 1 is equal to 0 modulo d, and we know that r minus 1 is equal to 0 modulo d. so that is divisible by d. And that means that if we write our number in the base r representation, then that is equivalent modulo d to the sum of the digits in the base r representation, and that means n is divisible by d if and only if the sum of its digits is. And finally, we can also have an analog to the result for 7, 11, and 13, and that is if d divides our base plus 1, then an integer n is divisible by d if and only if the alternating sum of its digits in the base r representation is divisible by d, and that sums up both the result for 11, where we talked about base 10 digits, as well as the result for the blocks of base 10 digits, because that's where the expansion base was just 1000, right? Proof? Well, hey, we prove by induction that for all non-negative j, we have that r to the j is equivalent to negative 1 to the j modulo d. And the base step for j equals 0 is trivial again. For the induction step, we have that r to the j plus 1 is r times r to the j. And we know that because d divides r plus 1, that means that r minus negative 1 is divisible by d, and that means that r is equivalent to negative 1 modulo d, and r to the j is by induction hypothesis equivalent to negative 1 to the j. And so that means this is equivalent to negative 1 to the j plus 1 modulo d. And that means that if I take my number in the base r expansion, then that is equivalent to the alternating sum of the digits in the base r representation modulo d. And that means that n is divisible by d if and only if its alternating sum of base r digits is divisible by d. And that should be it for divisibility tests. So that gave you an overview of the divisibility tests that you hopefully have learned in school, namely the ones for 2, 4, 3, and well, then anything else. 6 and 9 you can piece together from that, 4 and 8 you can piece together from that, and the divisibility test for 5 is quite simple, so you can also work out where that fits in with these theorems. And then you've got a little bit of background how to get a divisibility test by 7, by 11, or by 13, and if you have learned some of those divisibility tests in school and still remember them, congratulations, that is certainly not bad, and well, you can never not know enough. It's just that I didn't learn those in school, and I did okay too. Alright, so next thing is the perpetual calendar, and well, that ultimately turns into a vaudeville act, even though the history behind it is quite interesting. Because calendars are important to assure, for example, in agriculture, that crops are planted at the right time. Now, we take accurate timekeeping, especially timekeeping in terms of days, for granted, but it certainly was not always that way. And so here's the problem. The actual length of a year, the actual time that it takes for the Earth to orbit the Sun exactly once, is about 365.2422 days. The Egyptians had a year that had 365 days, and that eventually led to problems because, let's see, the Egyptian year was a little bit faster than the actual year, so ultimately the Egyptians' calendar got ahead of the actual year. And so that's where you can make jokes like, well, once they realized that it was snowing when it was snowing in July, they realized maybe something was wrong with the calendar. I'm not sure if that ever actually happened, but that is ultimately a legitimate problem. And so a little bit of that problem people were aware of in ancient Rome, and so Julius Caesar introduced the idea of a leap year every 4 years, and when you do that, then the average length of a year is 365.25 days, and that's of course really, really close, right? And so that means as long as your calendar predicted seasons all right in Caesar's day, then it still predicted the seasons all right 100 years later, 200 years later, 300 years later. But ultimately, that difference of merely 0.0078 days per year, that adds up. And so 1500 years later, that little difference has added up to 11.7 days. And because the actual year, which was shorter than what was recorded, passed faster than the calendar year, the calendar was behind. And that is a problem because ultimately in agriculture, especially in when you don't have advanced tools available, and in the harsher climes of Northern Europe, agriculture can become a race against time. Your crop isn't quite ready to be harvested, but weather is about to turn bad. What are you going to do? Are you going to harvest and have a crop that is not optimal in terms of individual fruit potentially being bigger? Or do you gamble? Do you let your crop ripen another week or so to hopefully get better individual grains, but at the same time risking it all because if a hard frost or a storm hits, you could lose it all? That is problematic, and that is something where literally lives hang in the balance. Now, I was blessed that I was born in the 20th century, and so in Europe that was not much of a concern, but the state of Prussia, and I was born in the former capital of the state of Prussia, had to deal with famines periodically, even in the 1700s. So this is something that is high stakes, not just in terms of money, it's high stakes in terms of lives. And so what they needed was a better calendar. And so in 1582, Pope Gregory set up a new calendar. October 5th, 1582 became October 15th. 1582, okay, so about 10 extra days had elapsed, right? So they didn't quite capture the 1 point whatever it was extra days, but that's not that problematic anymore because, I mean, you can just, ultimately, you just start planting 2 days earlier or so. At least I would hope that that was the solution. I'm not that versed in historical agriculture. And from there on out, basically they said, okay, every year whose number was divisible by 4 was to be a leap year, as before, except those divisible by 100, and those would only be leap years if divisible by 400. Now that looks really strange in terms of the numbers, but here's the reason. The average length of a year would now be dealt with on a 400-year time span, and so you've got 400 years at 365 days each, plus you've got 4 times 24 leap days, right, from the leap years. And that's because in a 100-year time span, of which there are 4 in a 400-year time span, you will have 24 leap days because you don't have the leap day in the years that are divisible by 100, except for one of them, which will be divisible by 400, and so that's that plus 1 here. When you do the arithmetic, and I admit without shame, I use the calculator, of course, you end up with an average length of a year of 365.2425 days. And so there remains a discrepancy of 0.0003 days per year. And that'll lead to a difference of 3 extra days in 10,000 years. So that is something that even on time spans that modern man is now comfortable working with, if we're looking at in terms of not just centuries but millennia, that's not going to make much of a difference. And so if we want to be a bit lax about that, we could say that still needs a fix, but we have a little bit more time to set it up, and hopefully 10,000 years from now human beings will have maybe even populated other star systems and will need different calendars for those stars. Okay, so now the vaudeville act behind that is, how do you determine what day of the week in a given Gregorian date is? So you now have to go with the Gregorian calendar, which is named after Pope Gregory there. And well, what do? You say that K will be the day of the month, M is the number of the month, where the months are numbered so that March is the first month and February is the 12th month, and that's because leap days are added to February, not December, so we want to make sure that the cutoffs are all correct. And then N is your year, where N is of course 100 times the century plus the year within the century, so again division algorithm. And your baseline data is that the 1st of March in the year 1600 was a Wednesday. And that is something that you can either reverse engineer from today's date using the process we're about to describe, or you could use historical records, right? And historical records have been kept, and so there are churches all over Europe that can tell you what day March 1 of 1600 was. There are newspaper archives, which of course are by now so treasured that you will not be allowed to touch the individual newspapers, but they may be able to show you some kind of record there still. Okay, so if we want to work out the day, the first step now is to work out the day d sub n of the week that March 1 falls on in the year n. And so if year n is not a leap year, then dn is of course recovered from dn minus 1 by adding 1. And of course you go modulo 7 because days go modulo 7. And that's because the 365 days in a year that is not a leap year are 52 times 7 plus 1 days. If the year n is a leap year, well, then you have to add 2 to the day that it was in the n minus 1st year, modulo 7 again, because 366, sorry. And again, we're back, and yeah, 366 is 52 times 7 plus 2. Alright, so now we're going to let x be the number of leap years between year n and the year 1600 for which we have our baseline data. Well, so what would x be? X would be that we take the number of our year, subtract 1600 off of that, and divide by 4, and take the greatest integer below that, because that'll sort of be the number of leap years between 1600 and the current year, except that we have to take out the number of leap years that were skipped, which is the current year's number minus 1600 divided by 100, and again we take the largest integer below that, and then we have to add in the leap years that were meant to be skipped but weren't skipped, if you will, right? The one that come around every 400 years. So if you take the number of the current year, subtract 1600, divide by 400, and take the greatest integer below that, that gives you the ones that were thrown in. Of course, here we're automatically also assuming that we know that, for example, the year 2000 was one of those leap years that was divisible by 100 but wasn't skipped, and that is something that you can look up, I don't know, on your computer in a calendar by now, because that calendar was made after the Y2K bug had all those strange scares and all that. Okay, so now we want to simplify this a little bit, and what do we get? If we break this apart, of course, 1600 divides nicely by 4, so that just gives you 400, so keep minus 400 in mind. That's all going to be absorbed in here, but we keep n over 4. Well, similarly, we keep n over 100 and n over 400, right? But what do we have? We get a negative 400 from here. We get a minus, so a plus 16, and negative 400 plus 16 would be negative 384. And then we get a minus 1600 over 4, which is 4, so a minus 4, which gives us a minus 388 in the back here. And if we now want to turn that into stuff that works with the century and the year, then we realize that the number of our year is 100 times the number of the century plus the modulus that remains, and we plug that in up here. And what does that give us? Well, again, we end up with a bunch of stuff that works nicely because a bunch of stuff will divide. So we keep a y over 4 from the first, we keep a minus y over 100 from the second, and we keep a plus y over, okay, this one we'll have to deal with a little bit more. And we also keep the negative 388. What do we have here? We've got 100c divided by 4. Well, that's 25c, so all this is an integer, so we can split that off, and we get 25c. Well, we end up with 24c in the end, because we end up with a minus c from here, because the fractional part is in the y over 100. And then we have plus 100c plus y divided by 400, and here's where both divisions could give us fractions, so we keep the c over 4 and we keep the y over 400. But what do we know now? The y is a number between 0 and 99, so that means this quotient is smaller than 1, and its greatest integer below that quotient therefore is 0, so that one goes away. And c over 4, now that one goes in increments of a quarter, and because y over 400 is smaller than a quarter, this one here isn't going to change the greatest integer below this one. So we end up with ultimately y over 4, this one's gone, plus c over 4 because this one's gone, plus 24c minus 388. And that's that offset x. That's the number of leap years that we have between March 1 of 1600 and March 1 of the current year. And then, because we're interested in this going modulo 7, well, we don't know what y over 4 is going to be, we don't know what c over 4 is going to be, but we know 24 is equal to 3 modulo 7, so that works out nicely, and that's because 24 is 21 plus 3. 388 takes a little bit longer, and well, let's see, 364 was divisible, but no, wait. 364 was not divisible by 7, so let's see, 350 is divisible by 7, leaving us with 38, and that you get 35 and you end up with 3. Yeah, sure. Okay, so that means now that the day of the week that March 1 falls on in year N is the day it fell on in 1600, plus the difference between the current year and 1600 because it advances by 1 every year, plus x, which is the number of leap years because that's where we have an extra one added in. And so that would be that the March 1st was the third day of the week if you start counting with Monday, so D1600 is 3. N is 100c plus y, so that works out too, minus 1600 stays, and x is the formula that we had from the previous panel. And now we just add things up, and what do we get? Well, the 3's are going to cancel, the centuries are going to work out somehow, the 1600 is going to shrink quite a bit, and the y we're going to keep. So we would end up with, let's see, we kept the y over 4, we kept the c over 4, this 3 and this 3 are gone. 100 is negative 2 modulo 7, and that's right because 98 is 70 plus 28, and that's 2 below 100, so that works out, that's negative 2c. In 1600, well, let's just divide 1600 by 7 and see what happens, or what happens to the remainder. 16, okay, you subtract 14, you keep a 2. 20, you subtract 14, you keep a 6. And 60, yeah, 60 is negative 3 because the next multiple of 7 is 63, so then negative 3 gives us the 3 here. So that also works out. And now all we need is the offset for the month. And the offset for the month, according to a mathematician named Zeller, is the largest integer below 2.6 times the number of the month minus 0.2, and there's no magic in there. He basically did some curve fitting through 12 points and tried to make it as simple as possible, and basically therefore he tilted that line until the line gave the right number for every single month. And so that means W, the weekday for the kth day of the nth month, remember March is the first month however, of the year 100c plus y on the Gregorian calendar is k plus 2.6 m minus 0.2, greatest integer below that, minus 2 times the number of the century plus the number of the year once you've ditched the centuries, plus 3 plus the number of the year divided by 4, greatest integer below that, plus the number of the century divided by 4, greatest integer below that, modulo 7. And so no wonder that at some point in time was a vaudeville act, because even once you know the formula, it takes quite a bit to do that computation quickly in your head. Okay, so let's now start looking at actual applications that are still being used to this day. If you want to schedule in teams to play all possible one-on-one matches exactly once in n-1 rounds, and then of course if you do home and away games, you schedule 2 times n-1 rounds. That's how European soccer works, if you're following that, for example. Well, if n is not even, then not every team plays every day, right? Because if you got matches where one team plays another team, your number of teams is divisible by 2, or one team sits out. So you would create a dummy opponent, which you could call bye. And so this is, for example, why just about any European soccer league that I am aware of has an even number of teams playing, unless something happened to add an extra team in there, which is not unheard of in Europe, but typically people try to avoid it. That's of course also the bye that you see, for example, when you are following North American football, where every team has a bye week throughout their season, but of course that scheduling is different because it's not a round robin tournament. Okay, so you create this dummy opponent, this bye, and for mathematical simplicity, let's just name the teams from 1 through n. And in round k, where you're playing n-1 rounds, so k is a number between 1 and n-1, teams I play as team j if and only if their sum is equivalent to k modulo n-1. Okay, so that's the rule. Why does that rule work? Why does that rule work? And first of all, what are the exceptions? Well, the nth team that you have, or the bye week, that plays the unique team so that 2 times I is equal to k modulo n-1. So now no team is scheduled to play 2 teams in the same round, because if I plus j is equivalent to k, which is equivalent to I plus j plus 1, where j now could be I also, that being equivalent modulo n-1 would mean, because you can cancel the I, that j is equal to j prime modulo n-1. And so that means if team I were scheduled to play 2 games, it would have to be with teams j and team j prime, or it could be scheduled to play as well as have a bye week in either week. That does not work out. J, your opponent, has to be unique modulo n-1, and we only have we have unique opponents modulo n-1, because then the team that is named n could also be named team 0. But of course, who would want their team be named team 0? You want to be number 1 in sports, not number 0. And also, the other thing you have to be careful is that no games are repeated, and no team repeats a game in the rounds from 1 to n-1, because if you have I plus j equals k, so this game I versus j is played in round k, as well as I plus j being k prime, meaning I versus j is also be played in round k prime, both equalities modulo or equivalence modulo n-1, that would mean that k is equal to k prime, or equivalent to k prime modulo n-1, and that can't be, because k and k prime are both between 1 and n-1. Okay, and that's already it for the round robin tournaments. Isn't that nice? That took a whole lot less than all the other stuff, and we even had a proof. Now, for the hashing functions, we're not going to go through the proof. We're just going to explain how hashing works and why it's needed. So customary identifiers are often too large for storage because, for example, when you've got a database, student records can be stored by social security numbers. Now, with concerns about identity theft, that is now certainly very much discouraged. But, well, all that means is that students are given a student ID number, and very often that number is very similar to a student ID number, to a social security number. So, for the time being, let us just assume that things are stored by social security number. Well, social security numbers have 9 digits, and no reasonable database will have 1 billion entries to accommodate 100,000 students. I apologize, my phone is ringing. And we're back. So let's look at this again. Social security numbers have 9 digits, but no reasonable database has 1 billion entries to accommodate something like 100,000 students. Now you might say there is no university, or at least there are very few universities that have 100,000 students enrolled at the same time, and you would be right. But even mid-sized state institutions that enroll 10,000 students at a time will maintain records, of course, also after the students have graduated. And if we're now looking at a perfect world where you've got 10,000 students coming in every 4 years and also graduating on time, which would be downright wonderful, and if you go with that over 40 years or so, then you have 10 times 10,000 students that you need to keep records of, and that's exactly the 100,000 that I came up with here. So this number is not outrageous even for comparatively small schools. Alright, so that means the line numbers in these databases that are given by social security numbers must be translated or hashed, as computer science people say, into smaller numbers, so that it's at least unlikely that different numbers get the same line. That way records can still be retrieved fast when the social security number is known. You just have to wrap that number somehow. And so basically the idea is you take hashing functions that have an input number k, such as a social security number, and they output the least possible residue of k modulo m, and that's the line number. So h of k is equivalent to k modulo m. That m should be chosen so that the outputs distribute reasonably uniformly from 0 to m minus 1. And for many reasons, which I'm not going to go into detail on because I am not sure I could explain them all because I don't know them. Remember, I play a number theorist on this show, but I am not a number theorist. But so for many reasons, actually, m should be a prime number that is slightly smaller than the number of allocated storage spaces. And, well, clashes can still occur, of course, and the simplest resolution is that when there is a clash, the clashing records are stored in consecutive lines or in special locations such as what's left over at top here. And that means double checks and searches still need to be performed when a clash has to occur, but the retrieval will point to the first of the clashing records. And, well, then the sequence of alternative storage spaces needs to be searched afterwards until the right record is found. And that can take a while, because if you've got, say, 110,000 lines for 100,000 students or for 100,000 entries, the likelihood of a clash still is quite large. And, well, can't we just assign more memory? Let's look at practical considerations here. For small databases, that certainly could be an option, but let's take a look at bigger things. So, for example, Social Security Administration, and assume that each record is 1,000 bytes. 1 billion records would require a terabyte, and as I typed that, I realized 400 million, okay, and 400 billion records would require half that with hashing. And okay, so that's both still feasible with today's hard drives. You can buy hard drives like that size in a store now. However, there are other projects that are going on right now, such as an envisioned national medical database where records can be really large, including scans of x-rays and the like, which would, as they're stored as JPEGs and the like, still would be pretty huge because you want to have good resolution on that. Now, that is envisioned because certainly some people have concerns about privacy and the like, but at the same time, the advantage of such a database would be, and it has to be weighed against disadvantages regarding privacy, the advantage would be that your whole medical history would be available to any treating doctor, including when you need emergency treatment, and so on. And so that database with 400 million records that are all big would be 400 million times big. That thing would be huge. And so that means better storage can still only, but it could reduce the size by half, and that means that costs for certain pieces of hardware like the servers and the drives and those things would be reduced by half. And well, personal opinion again, if I can get something at half price using legal and established and valid methods, I'll do it, and I'll do that in any economy. Maybe 20 years from now, technology people will laugh at me saying that, because storage space and hard drive capacity and all that is getting cheaper. But hey, I would still argue half price is half price, right? Okay, so how does hashing then turn into something like double hashing? You take the original key, and that would be a social security number or similar, and that is k, and when m is a prime number close to the number of record spaces, that already helps distribute the records evenly, and m times m minus 2 is larger than the record spaces. And, well, your first hashing function then is h of k equals k modulo m, or equivalent to k modulo m. your second hashing function is g of k being k plus 1 modulo m minus 2. And your storage space assignment is that hj of k is h of k plus j times g of k modulo m. And so because m is prime, you have that g of k and m have greatest common divisor 1, and that means the sequence hj runs, if necessary, through all numbers 0 through m minus 1. And that means all storage spaces ultimately will be assigned after clashes and everything. So that really is something that the last one would have to probably run through a lot of stuff, but everything will be assigned. And the retrieval speed, of course, depends a little bit on how many clashes there are. The fewer clashes, the fewer consecutive searches, and there are then arguments that show that this actually in some ways keeps the number of clashes rather small for every individual record under reasonable assumptions. Okay, and so now we come to check digits, which are actually in some ways a flip side of hashing, even though they are not directly related, and that is, as you keep records, mistakes happen. And the most common mistakes when entering or transmitting numbers are to change one digit or to transpose two digits. And that is just something, of course, that's not a mathematical statement. I think that is something that people would have to see through observations, but of course it's a very simple psychological experiment that could be set up. You let people type sequences of digits and figure out what the most common mistakes were. And to safeguard against these problems, people use check digits. And for a string of bits, for example, the binary sum could be a check digit. And then there are further codes, because of course there could be worse mistakes happening in electronic transmissions, but that is something that is being done as data is transmitted in binary form. And that safeguards against 1, 0 being changed to a 1 or vice versa. And that's the most common error in transmitted binary data. For 10-digit ISBN numbers, which are strings of digits x0 through x10, it turns out that actually only the first 9 digits encode the book, because ISBN is the code that you've got on the back on any printed book. The 10th digit is a base 11 number, where x denotes 10. Well, that's just the Roman numeral, and so every so often you probably find an ISBN code where the last quote-unquote number is an x. This is why. And that number is chosen so that the sum j equals 1 to n of j times xj is equivalent to 0 modulo 11. And the reason why that is now nicely workable is that if you take two 10-digit numbers in base 11, and so those are sequences of base 11 numbers, so that the first 9 numbers in each sequence are between 0 and 9, and so that the sum j equals 1 through 10, jxj equals 0 modulo 11, and so that either the second number, y1 through y10, differs from x1 to x10 in exactly 1 digit, or y1 through y10 is obtained from x1 through x10 by transposing the ith and jth digits, which are not equal, because of course if you transpose equal digits, nobody will ever notice. Then we have that the sum j equals 1 through 10, jxj is not equivalent to 0 modulo 11, and that means any double check, a very simple double check that can be performed with a computer when you type in a search by ISBN number, for example, can say, yeah, you didn't type in a valid ISBN code. Okay, so how do we prove that? Well, case 1. Say that y sub j0 is equivalent to x sub j0 plus d modulo 11, where d is a number between 1 and 10, right? And that's as far as that can wrap. Well, then you have that the sum j equals 1 to 10, jyj, is the sum j equals 1 to 10, jxj plus j0 times that extra d. And that's equivalent to j0d modulo 11. And that is because this here is equivalent to 0 modulo 11. And I claim that j0d is not equivalent to 0 modulo 11, and that is, well, because that would mean that the product would be divisible by 11, and neither of these two numbers is 11, or a multiple of it. Okay, in case 2, say the j1 and j2 digits with j1 not equal j2 have been transposed. Well, that means that yj2 is xj1 and yj1 is xj2, and all other digits are equal. And again, we look at the checksum of jyj from 1 to 10. Well, then that is the sum j equals 1 to 10 jxj, but now that means that the j1th digit is off by xj2 minus xj1, right? Because that j1th digit was yj, and yj is xj1 plus xj2 minus xj1, and it's off by j2 times xj1 minus xj2 because yj is xj1 is x because yj2 is xj2 plus xj1 minus xj2. Okay, you can work that out for yourself, and well, that is equivalent because again this sum is equivalent to 0 modulo 11. This is equivalent to j1 xj2 minus xj1 plus j2 xj1 minus xj2, and that's not equivalent to 0 modulo 11. And that is because if that sum was equivalent to 0, then we could just bring, let's say, this term to the right side, and all of a sudden both sides have a term xj2 minus xj1, and we could cancel that because we're going in arithmetic module 11, and this difference of digits will not be a multiple of 11, and that would lead to j1 equals j2 modulo 11, and then, of course, because again the numbers of the digits are between 0 and 9, that would end up giving us that, or between 1 and 9, that would give us that j1 is equal to j2. And that's the end of it, at least for these applications of congruences. Now, of course, there are more applications of congruences. In some ways, the remainder of this course is mostly all sorts of sophisticated mathematical applications of congruences. But here you have another piece of advanced mathematics, namely congruences, where you can now, in daily life, explain to people that congruence is used, for example, in making sure that ISBN codes are transmitted correctly, or at least that the most typical mistakes that human operators would make are not being made when ISBN codes are being detected when ISBN codes are being typed into a machine. Of course, if you compute in computer science, you will see a lot more about hashing functions. If you are in some ways in charge of a recreational sports league, you now know if you want to set up a round-robin tournament, how to do that. And well, the divisibility tests, that's something where we just know a little bit of background. I could compute on what day of the week I was born. I'm not too worried about that. I'm just glad that I've been born and that I am living this life. And right now, because this was a rather lengthy presentation, I think we're both ready to continue living this life, even though you probably also have some homework problems to tackle. So get to that.